Hi friends. Welcome to my channel. Please like the video and subscribe to my channel, if you like the video. In this video we will discuss about the topic, theory of simple bending, from the subject, strength of materials. Slide 1. Theory of simple bending. Whenever a beam is loaded, it is subjected to shear force, bending moment, and twisting moment. Analysis of these three parameters combined makes the problem difficult. So, to simplify the problem, apply loading on the beam in such a way that, both the shear force and twisting moment in the beam becomes zero. Now, the beam will be subjected to only bending. This condition of beam subjected to only bending is called pure bending condition, and the theory behind this is called theory of simple bending. Slide 2. Now, the question arises, how to get this condition on beam subjected to only bending. For that, consider a simply supported beam with loads as shown in the figure. Shear force diagram and bending moment diagrams are drawn. Consider zone CD in the beam. In this zone, shear force is equals to 0 and bending moment is constant of magnitude P times A. This zone CD in the beam is only subjected to bending moment and no shear force. Slide 3. Now, to make twisting moment equals to 0. Consider cross-section of the same beam. Centroidal axes of the beam are shown as blue lines. If the load applied doesn't pass through the centroidal axis, there will be some eccentricity of load. This case will further results in development of twisting moment of magnitude P times E, where E is the eccentricity in the cross-section. Eccentricity is the distance between load axis and centroidal axis. Centroidal axis is shown in blue color and load axis in green color. So, for zero eccentricity, apply load through the centroidal axis shown as red color. Slide 4. Assumptions made in theory of simple bending. Assumption 1. Material is homogeneous and isotropic. The property of a material which exhibits same characteristics at different points in any one direction is called homogeneous material. The property of a material which exhibits same characteristics at a points in any direction is called isotropy. Here, we assume material is homogeneous and isotropic. That means the material exhibits same property at all points in all direction. Assumption 2. Modulus of elasticity value in compression is same as in tension. Assumption 3. Plane section before bending remains plane even after bending. Assumption 4. Beam is initially straight and all the longitudinal fibers bend in circular arcs, with a common center of curvature. Assumption 5. Radius of curvature is very large compared with dimensions of cross-section. Assumption 6. Each layer of beam is free to expand and contract, independently the layer, above or below it. These are the assumptions made in theory of simple bending for further analysis. Slide 5. We are deriving equation for theory of simple bending. This figure shows, longitudinal section of beam before bending. AB is the top fiber of the beam. CD is the neutral fiber of the beam. EF is the bottom fiber of the beam. Slide 6. This slide shows the shape of beam, before bending and after bending. Load is applied from top. So, beam will bend in the downward direction, as shown in the figure. Green lines show shape of beam before bending as A, B, E, F. Red lines show shape of beam after bending as a dash, B dash, E dash, F dash. Length of top fiber AB is reduced after bending, as it is subjected to compression. Length of bottom fiber E, F, is increased after bending, as it is subjected to tension. There will be one such fiber, which is neither subjected to compression nor tension. This fiber or layer is called neutral layer. Therefore, all the fibers above neutral layer are subjected to compression, and below neutral layer are subjected to tension. Slide 7. By assuming the bent beam is in the shape of arc of a circle, extending both ends of the beam till their intersection, the angle subtended by these lines is taken as theta. Radius of circle is taken as r, as shown in the figure. Consider a section at a distance of y from neutral axis as shown as purple line in the figure. From the properties of circle, we have, length of an arc is given by r times theta. Slide 8. Now, we can write. Length of arc CD is, r times theta. Length of arc GH is, r plus y, times theta. Consider the bottom fiber EF. Length of bottom fiber has changed from EF to E dash, F dash. We know, strain is the ratio of change in length to its original length and is denoted with epsilon. Here, change in length is E dash, F dash, minus E, F. And original length is EF. Substituting these in the strain formula, we get epsilon is equals to E dash, F dash, minus EF. Divided by EF. Slide 9. Before bending AB is equals to CD, is equals to EF. Substituting EF equals to CD in the strain equation, we get epsilon is equals to E dash, F dash, minus CD divided by CD. Slide 10. We know, length of arc E dash F dash is, r plus y, times theta and length of arc CD is, r times theta. Substituting these values, we get epsilon is equals to r plus y, times theta, minus r times theta, divided by r times theta. By simplifying we get epsilon is equals to y by r. This is taken as equation A. Slide 11. By Hooke's law. With an elastic limit, stress is directly proportional to strain. Which gives, stress, sigma, is equals to modulus of elasticity, E, times strain, epsilon. Further, epsilon is equals to sigma divided by E. Substituting this in equation A, we get, sigma by E is equals to y by r. By rearranging, we get, sigma by y is equals to, E by r. This is our equation 1. Slide 12. Now consider cross-section of the same simply supported beam. The line joining locus of all the neutral layers is called neutral axis. Neutral axis is shown in the figure. Consider a strip at a distance of y from neutral axis. Thickness of strip is dy and area of strip is dA. From equation 1, we have, sigma by y is equals to E by r. By rearranging the terms, we get, sigma is equals to, E times y, by r. We know, stress is force acting per unit area. From this force is equals to stress times area. Now, force in the strip, dF, is equals to, sigma times area dA. Substituting stress formula, we get, dF is equals to, E times y, by r, times dA. Total force can be calculated by integrating the above equation of force in the strip. Slide 13. In total force equation, E and R are constants. So, taking them out, we get the equation as shown. F is equals to, E by R, into, integration of dA times y. Slide 14. We know, total moment in the cross-section is given as, force times perpendicular distance. Perpendicular distance of considered strip is y. Substituting force value in the moment equation we get this equation. Total moment, m is equals to E by r, into integration of dA times y square. Slide 15. As we know, integration of dA times y square is called moment of inertia and denoted with capital I. By substituting this in the above equation we get, m by I, is equals to E by r. This is considered as equation 2. Slide 16. Equation 1 and 2 are shown here. From equation 1 and 2, we get m by I, is equals to sigma by y, is equals to E by r. This is the equation for pure bending. Where m is the bending moment. I is the moment of inertia. Sigma is the bending stress. Y is the distance of considered fiber from neutral axis. E is the modulus of elasticity or Young's modulus. R is the radius of curve. Thanks for watching the video. Please like the video and subscribe to my channel if you like this video.